a postdoc at RMIT, and I did my PhD here at Monash, and my work involves mathematically modeling and computationally simulating how tiny things interact with light. And today's talk is going to be on this topic, nitrogen-vacancy plasmonics, which is about how a tiny quantum system in diamond called the nitrogen-vacancy center interacts with what's called plasmonic nanoparticles that we'll be talking about, and how both these interact with each other and with light. Today we're going to be talking about NV-plasmonics, and this is the outline of our talk today. So I'm first going to walk you through a little bit about the nitrogen vacancy center, which, as I said, is a quantum system, which is a defect in diamond. And then we're going to look at what plasmonic nanoparticles are, and we're going to talk a little bit about why they're really amazing, both these types of particles, why they're really amazing on their own. And then we're going to talk about NV-plasmonics, why we can put them together and get even better results for some kinds of applications. So let's first talk about the NV center in diamond. Now I'm going to start by walking you through one of its many applications so that we can start with an appreciation for the practicality and the versatility of this quantum system, which can even operate at the room temperature, unlike many other kinds of quantum systems. So back in 2005, two scientists named Chernobrod and Berman made the seminal proposal for what we call scanning probe magnetometry, or scanning probe microscopy today. And this is the schematic of their seminal proposal. And basically what they said was, they said if we could attach a single nanoprobe that is thousands of times, perhaps 10,000s of times smaller than the width of a human hair, to a tiny cantilever that's a bit comparable in size. And if we had a way to couple a laser beam to this setup, and also an RF field or a microwave field, depending on the application, and optionally we could even have a permanent magnetic field to intensify any magnetic field changes that we want to sense. And we also need a way to detect the photons that are given out from our sensor. So if we could have a setup like this, they said it could go extremely close to tiny magnetic samples and do high resolution scans and measurements of things like different ferromagnetic materials, single spins, proteins, molecules, and whatever you could put on a slide and take the magnetic probe to. So this was a fantastic proposal, but by the time they proposed this, scientists were not very clear of what type of sensor to use at that nanoprobe tip. But within a few years, they started picking things up. Fast forward a couple of decades, the proposal has become a reality today thanks to a sensor called the NV center. And these kinds of setups are available around some laboratories around the world today. And this is a picture of a scanning probe microscope in a laboratory. Now I'm a theorist, so I don't get the opportunity to play with this kind of cool equipment myself. So I like visiting experimental laboratories, talking to a lot of people and taking pictures like this one. And here's a picture that I took myself. So my colleagues can keep their magnetic samples on this place called the sample stage, send and collect light from this confocal setup, and they use this thing called the tuning fork to take it very close to the magnetic samples and do their scans and measurements. Now to give you an idea of the length scales of measurements that we're talking about here, here is the tuning fork. I'm holding it in my hand here so you can get an idea of its size. Now if you zoom right onto the tip of it, this is what it's going to look like. So this is a metal bit. So it's a few millimeters long, and at the end of it there is a small silicon tip that's less than about 1 millimeter in size. And if you zoom right into the tip of that silicon tip, this is what it's typically going to look like. So this is the end of this silicon handle or tip. At the end of it there's a few tens of micrometers long diamond paddle. And at the very end of that diamond paddle there's a tiny diamond tip, and if you zoom onto that, this is how it's going to look like. It's just a few hundreds of nanometers, this scale bar. And at towards the very end of that diamond tip, perhaps about 10-ish nanometers away, there is a tiny quantum sensor, a single defect that goes close to whatever the magnetic sample that's kept here and does the scanning and the measurements. I think it's an incredible setup for people to be using based on the NV Center. And here's a picture of a magnetic field of a hard disk that has been scanned using a setup like this one. It can do scanning at an incredibly small scale, and I think this was taken back in 2012, and these setups have improved even further since. You can check out this paper if you're interested. It's a fascinating kind of equipment, I believe. And here's the sensor that made it all possible. It's a cartoon illustration of the NV Center. So it has an impurity nitrogen atom or an intruded nitrogen atom next to a vacancy or a missing carbon atom in the diamond lattice. So both the nitrogen and the vacancy are surrounded by the regular carbon atoms in the diamond lattice. And thanks to this very amazing sensor that can even retain its quantum operations at room temperature, a lot of breakthrough applications that can operate retaining their quantum properties at room temperature are emerging. And these include things like quantum computers that don't need to live inside refrigerators to keep their qubits alive, being manufactured right here in Australia by Quantum Brilliance. And then we have scanning probe magnetometers that we just discussed, and these are also commercially available by companies like QNAMI and QZaber. And we even have things like lasers that can be controlled using tiny changes in magnetic fields. And these are just a few to name. This list goes on. And the way the NV Center operates in almost all these amazing applications apparently has one feature in common. And that is, it takes in a high frequency beam of light, typically green light is used, as the input, and it emits a beautiful pink aura, a glow, which is comprised of red photons as the output. And the brightness of this glow depends on what we call its quantum spin state. And this spin dependent brightness is the basis of many NV applications, although not all. So it's worth looking a little bit into the spin dependent brightness, and that's what we're going to do next. To understand how the spin dependent brightness happens, let's first see how the NV Center gets its spin. So the NV Center, particularly the NV- center, which is what we usually refer to when we say NV Center, because the NV- is the most useful for many applications. So it has two electrons coming from the nitrogen atom, two valence electrons, and then we have three valence electrons coming from the carbon atoms surrounding the vacancy, which are bound to nothing because vacancy is just a missing carbon atom. And one electron, one valence electron, is captured from the lattice, and this is typically from a nearby nitrogen donor, and this extra electron is what gives the NV Center its negative charge. And these 6 outermost shell or valence electrons live in 4 orbitals, and these are the names of the orbitals. And here's how the energies are arranged with respect to the conduction band and the valence band of the diamond host the NV Center lives in. And what you see here is the ground state electronic configuration of the NV Center. Now, if you have a closer look at this configuration, the bottommost A1 orbital has a pair of electrons, and then A1 again has a pair of electrons, and EX and EY, these two degenerate orbitals, has only one unpaired electron each. And it's the spin of these two unpaired electrons that contribute to the overall spin of the NV Center, or the overall spin angular momentum or magnetic orientation of the NV Center. So if both these unpaired electrons are spin up, or in other words aligned along the NV axis like two tiny compass needles, the NV Center gets a spin of 1 overall. If both of those are pointing downwards or spin down, the NV Center gets a spin of -1 for its triplet state. And if one is up and one is down in either way, it gets a spin of 0. And so these are the spin quantum states, and the energies of these spin quantum states are sensitive to a range of factors like the electric field incident on the NV Center, the magnetic field, even the temperature and the strain or the pressure that is applied on the diamond lattice can change the energies of these levels. And that makes the NV Center very versatile and useful for many kinds of sensing applications, and that can sometimes be a little bit of a nuisance for the computing applications where these things could be considered noise. So that's about how NV center gets its spin. Now that we have some idea of that, let's see how it gets its spin dependent brightness, which is kind of the superpower of the NV center. Now we're going to use this very simplified level structure to understand how this spin dependent brightness happens. In reality, the level structure is much more complicated than that, but this is enough for us to understand the gist of what's going on. So let's assume that the NV center has an optical ground state G, which is a spin triplet comprising the states that we just discussed, the spin 0, +1 and -1, and plus and -1 are usually degenerate if nothing is disturbing the NV center too much. And again, the excited optical state has the same 3 spin levels, at least in the ground state. This is a good enough approximation. Now, if we excite the NV center with high enough energy light, higher than its 0 phonon line, typically it's green light, it will make a transition from the ground state to the excited state without any change to the spin. And once excited, it has 2 competing pathways to come back down. The first is to come back down while giving a red photon out to its spectrum, emission spectrum, and both the radiative transitions preserve the spin. That doesn't do any change to the spin. But there's also a non-radiative transition pathway, which is called intersystem crossing, and it flips the spin. It predominantly happens from these plus or minus 1 levels in the excited state back to the spin 0 of the ground state. So some of you may have already guessed that if we send the system up from the spin 0 state, it's more likely to come back down giving out a photon, and when we send the system up from here, a significant amount comes back down without giving out a photon. So if the NV center is in the spin 0 state, it looks a tad bit brighter, or more photons are given out than when it's in the spin plus or minus 1 states. So we call this state, the spin 0, the brighter spin state, and these 2 states, the other 2, are called darker spin states. And another point that I should make here that will be useful later in the presentation is that if we keep shining this pump for a while, long enough, and by that I mean about few microseconds in NV terms, all the spin is going to be predominantly populated to the spin 0 state, because whatever goes up here comes back down, and whatever goes up here, significant portion comes back down to 0. So after a while, it's all circulating among the 2 spin 0 states. So let's keep that in mind for later. Right. So let's have a closer look at the spin subsystem. This is the same thing here that I've drawn apart. If there's no static magnetic field around, we can use a microwave field to drive transitions between these, either from 0 to +1 and -1, and these 2 are usually the same level, so we're driving to both. So if we go scan in the microwave frequency, starting from a low value and going towards some high value, when we hit the right microwave resonance, we're going to be populating a lot of dark states, and that's why we see this drop in fluorescence. And now, if you go and keep your NV center at some place where you want to sense the magnetic field at, that's going to split these 2 degenerate levels apart. We call this Zeeman splitting. And that splitting is proportional to the static magnetic field along the NV axis, this axis. So if we now scan the microwave frequency, we're going to hit 2 places where the microwave matches this energy gap. And this gap between the dips is going to be proportional to these energies, so it's proportional to the magnetic field. So that's all we have to do if you want to sense a magnetic field, a static magnetic field, using the NV center. So you go and place your NV center or the tuning fork tip at the place where you want to sense the magnetic field at, and then you shine your green light onto the sample, including the NV center, and then you scan a microwave frequency. You measure the gap between the dips and convert it using a simple conversion factor to the static magnetic field you need to find. And this process is called optically detecting the magnetic resonance, or ODMR. And you can use variants of this to do vector magnetometry as well, but I'm going to skip that bit because this is going to suffice for the rest of the talk. And yeah. So that's all I wanted to share with you about the NV center. Here's a summary of what we learned. We learned that the NV center is a defect in diamond, with a nitrogen atom next to a vacancy, and it can absorb high frequency light and emit a beautiful pink glow, the brightness of which depends on the quantum spin state of the NV center, which can take 3 discrete values, +1, -1, and 0. And the energies of these are proportional to a range of things, which gives the NV center a lot of applications. Right. So that is about the NV center. Let's now talk about plasmonic particles. So plasmonic particles can typically be things like tiny pieces of gold or silver, or sometimes even materials like graphene that are thousands of times or perhaps 10,000s of times smaller than a human hair, or in the nanometer scale. Now I have a question for those of you who haven't heard about plasmonic particles much, if there are anyone that haven't. If you take a chunk of gold, a big chunk of gold, and go grinding it or crushing it down to smaller and smaller and smaller pieces until we reach the nanoscale, what color do you think that dust, or if we dissolve that, disperse that dust in water, what color do you think that water would look? And do you have any guesses why? A fine dust of gold, that's nanometer scale.
Purple.
Yes.
It's a guess.
That's a guess.
Yeah.
That's a very good guess.
Red.
Any other guesses?
It's black.
Black. Okay.
Blue.
Blue.
Gold?
Yeah, that's,
It would be red.
yes. It'll be purple reddish. It's going to be ruby reddish. So these are tiny gold particles dispersed in water. So about 5 nanometers on this end and about 100 nanometers in this sense. So this is a clear indication that these particles interact with light in starkly different ways from the chunk of bulk gold interacts with light, and also in slightly different ways from each other, because the color changes. The color is dependent on how they interact with light and what color is finally sent to our eye, right? So, and this is the reason behind it. So here's the typical absorption spectrum of gold nanoparticles. They absorb a lot of green light, and what we see here coming out, transmitted to our eye, is a lot of red and a bit of blue and violet that did not get absorbed. And what happens when the particle sizes went bigger is that this peak has seemed to shift towards the red side. So more red is absorbed, a bit more red is absorbed, and a bit less blue and violet is absorbed, which means we get it to be a bit more purplish as the size gets bigger. This is for gold particles, and it's a tad bit different for silver. And this peak happens due to a special phenomenon called localized surface plasmon resonance. So the peak is called a plasmonic peak. Let's have a look at what that is. So here's a gold particle. I've drawn it in gold only symbolically now, and it's going to be much smaller in size than any light, visible light that we shine on it, because this is micrometer scale and this is just a few nanometers, a few tenths of nanometers sometimes. So what happens when we shine light on it is that this gold particle has free electrons. The free electron, the sea of free electrons, couples to the electric field components of the light, and it oscillates back and forth as the electric field changes its sign. And it's as though the particle is experiencing the same magnitude or the amplitude of the field throughout, because the particle is tiny compared to the field. And this collective oscillation or wobbling of electrons back and forth is called a plasmonic oscillation. And the particle has to have a few special properties in its permittivity to show this behavior. Particularly, its permittivity should be should have the opposite sign compared to the medium that it is in, and it should absorb, dissipate only a very little amount of the energy that it takes in, so that it can use the energy for the oscillations. And this oscillation can happen very strongly with some colors of light with a big amplitude, and not so much with other colors of light. So in this case, it resonates with the green light and doesn't with the red light. And the resonant condition is what's called a localized surface plasmon resonance. And because of this, these particles can be really good tools to control quantum emitters that are kept nearby in the nanoscale, which is the regime where conventional methods of controlling light, like microcavities, for example, fail because of the diffraction limit. So they can control different properties of quantum emitters via 3 distinct ways. First, they can change the optical field by changing or scattering light kind of like a tiny dipole that changes its sign. And they can also change the rate of photon emission from the quantum emitter by changing what's called the local density of optical states around the emitter, which is how well the emitter's environment can absorb photons, because the particle is now part of the emitter's environment. And lastly, these are going to inevitably absorb some photons, which is where we have to be a little careful about when planning our emitter plasmonic systems, depending on how much photons we can afford to be absorbed by the plasmonic particle. So that's all I wanted to share about the plasmonic particles. To quickly sum it up, we learned that tiny particles of things like gold and silver interact with light very differently compared to the bulk material. Because of a special phenomenon called LSPRs, and these excitations make tiny gold and silver particles great tools to control quantum emitters like the NV center.
Could I interrupt you?
Yeah.
Do they have one plasmonic mode? It looks like a dipole oscillations, but do they have quadrupole oscillations and other modes?
They can have, as they get bigger, other modes as well. So now that we've learned about both the NV center and the plasmonic particles, we're going to talk about putting these two types of particles together, hoping to get the best of both worlds. So a couple of years back, we derived a quantum optical model for how an NV center interacts with a plasmonic particle. And what you see on the right hand side is the optical abstraction of the NV center that we used for this work. Now it has a set of ground states at different vibronic levels, and it has a set of optical excited states as well at different vibronic levels again. And here we've just defined the lowest energy excited state and a phenomenological upper excited level that's kept at the energy of the incoming light. We assume that this is the level the light couples to, and it represents everything above the lowest energy excited level. And you may have noticed that we haven't included the spin sublevels here, and that's because, as we discussed at the start, when we shine just a laser for a long enough time on the NV center, it preferentially populates the spin to the zero state. So we can get away with this simple model, at least as long as we're not shining any microwaves. Now let's have a quick look at how this model operates. If you shine light, it's going to drive transitions from the ground to excited. And once excited, it's going to quickly rattle back down at terahertz speeds to the lowest energy excited state, because that's where it's the most stable when in the excited level. It's going to stay there for a while for the photoluminescence lifetime and come back down, giving out a red photon to one of the side bands. And if there's any excess energy left, it's going to dissipate as heat in the ground state. Now we don't have to consider the intersystem crossing, because that happens predominantly from the plus or minus 1 states, which we are not giving any prominence in this model. Now if you keep a plasmonic particle next to the NV center, it mainly changes the rate of excitation by changing the green field amplitude, and it also changes the rate of decay in addition to absorbing some photons. So that's the gist of our quantum optical model for the NV plasmonic interaction. And it matched this controlled NV plasmonic experiment where this group has kept a single nanodiamond with a single NV center next to a gold particle and placed it around different locations and looked at what happens when we change the polarization direction. So this was the experiment, and this is a comparison of the experiment to the theory that we've derived. So these blue dots are photon counts given out by the NV center as the polarization of this green light is rotated using what they call the lambda by 2 wave plate. And this the solid pink line is our theory, and it matched fairly well, and there are some other verifications as well in the paper here. So this looked like a good enough verification to say that we could go ahead and try to make some new predictions. So here are some, then I'm going to share some new predictions that we've made. So we decided that we're going to just look at these two possible orientations just for the sake of simplicity, because these two are the easiest to model analytically. Other orientations can be done, but not as simply. This one is the brightest case orientation, and this is where the optical dipoles of the NV center and the plasmonic particle align along the same axis. And this is the darkest case orientation where the dipoles are tangentially aligned, and you'll see why in a minute. So we looked at different things like what happens when we change the size of the plasmonic particle, the distance, the permittivity of the submerging medium, and etc. So let's see what happens when we change the radius. In the first setup, if we go changing the plasmonic particle size, this radius Rm, the emission of the NV center enhances as the particle gets bigger. And this is because if you think about how the dipole field lines happen, the increasing plasmonic field goes through the NV center and it's along the same direction as the external field. So the resultant field gets larger as the plasmonic particle gets larger, which means larger excitation and hence larger emission strength. And in the other orientation, somewhat counterintuitively, when the plasmonic particle size gets bigger, the emission decreases. And that again can be understood just by thinking about how the field lines happen. This particle gets bigger, the dipole response field gets bigger, but it offsets a part of the external field at the NV location because it's in the opposite direction. So that's the simple reason for why this emission strength decreases as the plasmonic particle size gets bigger. And we also looked at things like what happens when we change the permittivity of the submerging medium. And apparently for both these setups, at least in the regime that we looked at, emission enhances with increasing permittivity. And this has to do with several reasons, including the reduction of optical screening experienced by the NV center inside the diamond lattice, enhancement of decay rates, and also some plasmonic effects. The plasmonic field gets larger, at least for the first setup. And these black dashed lines in all these plots, that's the emission of a single NV center inside a nano diamond that's kept in air, and that's our reference for this entire presentation that we compare everything against. Now you can find a few more results if you look at this paper if you're interested. Also do feel free to have a chat if you want to discuss anything in detail. So we discussed at the start that most of the interesting applications at the NV center are dependent on its spin, particularly the spin dependent brightness. So the obvious next step for us was to include spin in our optical model. So here is our spin included model for the NV center. This is just a combination of the earliest two-level simple spin based model that we discussed with the optical model that we just saw a slide or two back. So let's also have a look at how this operates. It again has these ground vibronic states and excited vibronic states. When we shine the green laser, it's going to drive transitions between the two. Terahertz scale decay back to the lowest energy excited state. It can come back down optically. Any energy that's extra is dissipated thermally. And now we have the intersystem crossing pathway because spin has been included here. Now each of these blue lines are separate vibronic levels, and in this model we model every vibronic level as a spin manifold with the +1, -1 and the spin 0 states. And this is where all the microwave and the Zeeman interactions happen. Now in the current model, we are only considering magnetic fields along the NV axis, and we hope to extend this to capture other magnetic orientations and the electric-like interactions as well. So that's about the NV abstraction of the spin included model. And I also want to quickly walk you through how we model the interaction between the excitonic particle and the plasmonic particle. For both the spin included model and the quantum optical model, it goes by the same concepts. Now I don't want you to worry too much about the mathematical expressions here. I just want to outline the simple steps that we took, but if anyone wants to discuss the details of math, I'm happy to catch you after the so what we first do is we first write down the Hamiltonian for the NV center, looking at it as a closed quantum system that coherently interacts with the total field that is incident on it. And what the plasmonic particle does here is that it changes the optical field incident on the NV center, and therefore it changes the optical Rabi frequencies, or the optical population oscillation frequencies of the interaction portion of the Hamiltonian. And then we look at the NV center as an open quantum system that evolves in time with its quantum properties gradually fading away because of its interactions with the environment. And we do this in what's called the Lindblad formalism. And the role of the plasmonic particle here is that it changes the optical decay rates of the NV center, and we take that into account when solving for the system. Now, after we've solved the master equations, we have the set of states as it evolves in time, and we can do a lot with that information. For example, we can calculate the optical photoluminescence spectra using correlation functions. We could do a time domain analysis. We could microwave frequency sweep steady state values and get audio mass spectra, and these are some of the things that we can do.
So is that through changing the Hamiltonian law?
No, we solve the master equation and then can find the correlation function and get the Fourier transform of that to get the photoluminescence spectra.
So it's in the time series that you...
Yes, yes. So after being able to do all that, we just wanted to see if the model actually works as we expect it to. So we compared the output from our model to a few different experiments in the literature, and here are some of the comparisons that we've done. So these are for just the NV center, for what we could find the experimental data for, and this is in the presence of a plasmonic particle. This is the same experiment that we compared against for the optical only model, because I couldn't find any other controlled experiment that could go with the single particle based modeling that we have at the moment. And then we wanted to see how a plasmonic particle could potentially help to enhance the spin readout of NV centers. And here are some sample results. Perhaps on the top left, you see a bit familiar signal. So this is the magnetometry or DMR signal for NV centers. If you remember, this gap between the dips is proportional to the static magnetic field along the NV axis when we do ODMR. And D is the depth from the baseline photoluminescence level to the lowest point, and B is the brightness. And we would like these quantities to be as large as possible so our signal can withstand a lot of noise. And this is the typical spin qubit readout signal. If you're using the NV center as a spin qubit, we get this top solid line shape if the NV qubit is in the spin 0 state when we start the measurement process, and we get this bottom dash line shape if it's in the spin plus or minus 1 states, which we can select as the bottom of the Bloch sphere. And this area A is called the contrast of this time domain reading, and B is the baseline brightness level. And again, we'd like these quantities to be as large as possible as well, to distinguish between the extreme possibilities and to withstand noise. And model predicts that if we keep about 10 nanometer silver nanoparticle next to the NV center at a high enough permittivity medium that brings the resonance of the silver particle towards the green region, which could be as high as the permittivity of diamond itself, we could get very high enhancements of these quantities like D, B, this A, and this B here. So these are compared to a single nano diamond in air, but if we compare to a bulk diamond, a single NV center in bulk diamond, these enhancements are going to be about 1/3 of what you see here, but I guess that's still going to be quite significant. And we hope to see what happens when we change the shape of the plasmonic particle as well, because that would allow us to have the resonance in green, which is the preferable region for excitation, without making the permittivity of the surrounding medium so high. And we hope to do that soon. So that's about it. Our spin included model can currently help to enhance some aspects of the NV center as a spin qubit and also as a magnetic sensor, and we have a bit more work to do here, which we're hoping to get done as soon as possible. And also hoping to capture the capabilities of the NV center to this model, like electric fields all the way to controlling nuclear qubits or hyperfine coupling, which is useful when using NV centers as buses for nuclear spin qubit based quantum computing. So plasmonic engineering could perhaps, when tuned correctly, help us to enhance a lot of NV quantum technologies, perhaps almost all of them, ranging from measuring activity inside cells like action potentials and different magnetic signals, all the way to controlling quantum computers of those like quantum brilliance, which are based on nuclear qubits coupled to NV centers. So that's about it, and I also quickly wanted to show you this. All the simulations that I showed you today are based on solving quantum master equations, which describe how a quantum system evolves in time. And we've recently written this tutorial with loads of code examples just to teach how to solve quantum master equations and do simulations like the one I just showed you. And Francesco, the first author of this, was also a Monash alumnus, Kavan's PhD student a while back. So some of you might know him well. So feel free to check that out if you're interested, and let us know your thoughts and comments. Finally, I'd like to thank all my co-authors of the work I presented today. Professor Jared Cole from RMIT, Dr. Francesco from University of Padua, and Professor Fedor Jelesko from University of Ulm, and RMIT and Exeter Science for funding, and Monash Physics. And thank you so much, Dimitri, for hosting me here today. And thanks everyone for the kind attention.
Welcome.
So there's another emission at the NV center at like 1 micron. Do you think that you could enhance that with gold particles as well?
Yeah, possibly, but for that we have to tune the resonance to match that gap. So it's not the same particle, perhaps, that can enhance both the optical transitions in one go. It'll have to be 2 particles coupled separately to the 2 transitions.
Could that have an effect on the total spin contrast and things like that? You make that transition faster.
It'll probably make it a tad bit worse because we have more photons coming out at the dip, which takes the dip higher. I believe it might make it a tad bit worse. I have to think about it a bit deeper though. There's a chance.
Let me ask. So I assume that lifetime of this excited state, this center, is huge. But what is lifetime for the plasmons in the gold? Does it reduce your coherence of your system?
The plasmonic particle is modeled classically here. It's basically modeled as a classical dipole, and plasmonic emission is not taken into account, as in the plasmon coming back and giving out a photon. That's not considered in the model. And it'll probably be not 100% sure of this number. I guess it's in the femtosecond range, the plasmonic emission lifetime.
Welcome for
Julie, I don't know if you'll know this because it's like more of an experimental thing, but like, do you know why the tuning fork thing is shaped like a tuning fork?
I'm not sure. I'm just guessing here. I think to go as close as possible. You mean the big chunk of it?
Yeah, like that you showed at the very start.
You mean before zooming in?
Yeah.
I'm not really sure.
Okay.